Okay, in this lesson we're going to be talking about factoring the difference of perfect squares. And the first thing I want you to notice is that word difference. That means subtraction. So you can only use this if there is a subtraction sign in there. And perfect squares, if you think about what those are, it's numbers like 1, 4, 9, 16, 25, 36, 49. You get them by squaring numbers. So like 2 times 2, 5 times 5. So those numbers are called perfect squares for a reason. Also, you'll need to think about variables. Variables, to be a perfect square, need to have an even power. And so let's get into some examples. The first one, you have x squared, which even power, and 36. 36 is 6 times 6, so it's a perfect square. This also meets the requirement that you have a minus sign right there. So this is exactly the kind of problem we're looking for. And anytime you have a binomial that is a difference of perfect squares, you're going to factor it into two parentheses. One of the parentheses you're going to put a plus in the middle, and the other you're going to put a minus in the middle. You're going to think about what breaks this apart, this x squared. When it's variables, you're going to end up with half of them here and half of them here. So x squared is x times x. Then think about the 36. What number multiplies by itself to get 36? And as we mentioned, that was 6. 6 times 6. So I'm going to put 6 here and 6 here. Okay, our next example, let's check all of our parts. We have 81, which is 9 times 9, so it's a perfect square. X squared, which is an even power, so we're good there. And 49 is 7 times 7, so that works out, and it has a minus in the middle. So I'm going to make two parentheses, put a plus in one and a minus in the other. It doesn't matter which one you put first, whatever works for you. And then you take your square roots. So the square root of 81 is 9, or 9 times 9 is 81. The x is with that, so you break it apart. You had 2, put 1 with each 9. And then your 49 is 7 times 7, so 7 here and 7 here. And you're done with that one. Now, if you look at number 3, it does have the minus, but the numbers 20 and 5 are not perfect squares, and the powers of your x's, 3 and 1, they're not even. So when you originally look at this problem, you think, I'm stuck, I don't know what to do. This is definitely not a difference of perfect squares. Well, this is where you have to remember that anytime you're factoring, you have to try to take a GCF out first. So what would the GCF be here? Well, between 20 and 5, that would be a 5. And between x cubed and x, it's an x. So our GCF is 5x. And if I take that out, 20 divided by 5 is 4. And I'm left with an x squared. And if I take the 5 out and the x out, that leaves me with a 1. So far, this 4x squared looks good. And you also have to remember 1 is a perfect square because 1 times 1 is 1, or the square root of 1 is 1. So that's going to work out. So how do you write this with a GCF? You just bring it down. You put 5x out front, and then you make two parentheses. And you treat this inside just like we treated the problems up here. So 1 gets a plus, 1 gets a minus. The square root of 4 is 2. And the square root of x squared, or break the x squared apart, gives you x and x. The square root of 1, or 1 times 1 is 1. So we put 1s back here, and this does not like hanging onto my x's. Okay, so that's our third example. Let's move on to some bigger powers. Everything we've done so far has been x squared, but 4 is an even number, so it will break apart. And again, 1 is a perfect square. We have a minus, so I'm going to go ahead and put two parentheses, put a plus and a minus. The square root of x to the 4th, or think about breaking it in half, gives you x squared. So I have x squared here and x squared here. And then the square root of 1 would be 1, so 1 times 1 is 1. And that's all you have to do there. Now, look at that answer. X squared plus 1 and x squared minus 1. 1 is a perfect square. X squared is an even power. Can this be broken down again? The answer is yes. Can this be broken down again? The answer is no, because of the plus. So this first parenthesis, you will bring it down like we did the GCF. But the second one, you can actually factor using perfect squares again. So we're going to put a plus in one and a minus in the other. And when I break the x squared apart this time, I get x's, which are single powers, and we will not be able to break those down again. The square root of 1 is 1. And so this is actually the fully factored form of x to the fourth minus 1. So let's try that again. Similar problem here. We have x to the fourth minus 16. So starting out, you have an even power and 16 is a perfect square. And there's a minus between them. So I can go ahead and at least do one perfect square line. And if I break the x to the fourth apart, or take the square root of x to the fourth, that's x squared. Put those in. The square root of 16 is 4, or 4 times 4 is 16. And I'll look at this. Is this the same situation that we had in number 4? And it is. Again, because this has a plus, I can't do anything else. That is all I can do. But because this one has a minus, 4 is a perfect square, and x squared is an even power, I can do the perfect square rule again. Make 2 more parentheses, put a plus and a minus. Then the square root of x squared, or break it apart, you get x and x. The square root of 4 is 2. And when you get to this level, that's it, because 2 is not a perfect square, and this x is not to an even power. So that's as far as you can go. Notice the similarities in those two. Okay, for our sixth example, we look at this. We have a perfect square, 4, x squared, even power, and 9 is a perfect square. However, it has a plus right here. So what does that mean? It means I cannot factor. I cannot do what I was doing up here. It's kind of like this x squared plus 1 and the x squared plus 4. It's stuck. So if you get a problem like that and you're like, I can't even do anything, I don't even have a GCF, that's fine. It happens sometimes. You put not factorable. Now, we will be using this later and we'll be solving problems. So there may be more steps that I need you to take later on, but for right now, we're just going to say not factorable.